Okay, so here we go with the online-offline approaches. Yeah, the basic idea is, as I told you before, that we have a two-stage algorithm or a concept. So two phases, an online phase or online component, where we maintain a large number of small cluster summaries, so-called microclusters, and an offline component where we can at an arbitrary time point generate the actual clustering on the microcluster information that we maintain in the online component. And the microclusters are there to reduce the data, obviously, and by reducing the data, of course, we want to keep sufficient details. So we want to maintain some kind of, we want to summarize the data, but still keep some sufficient details, some sufficient information in order to do the clustering afterwards in the offline phase. So we should separate clusters from noise for improved robustness, and we should try to provide accurate and fine-grained input for the further steps, including the offline phase. Yeah? And as I told you before, in the offline phase, we work on those summary structures and generate from the microcluster information a kind of macro clustering, which is probably only approximate, as mentioned here, because we work on summarizations, we work on aggregations of the raw data, because we cannot access the raw data anymore. But as long as the aggregations, the summaries, are accurate, the approximate clustering will be also quite accurate, at least. Yeah? Typically, the clustering method is quite exchangeable, so we are somehow model agnostic in that case. But we'll see that different summary or types of summary information are tailored to different clustering methods. Yeah? Individual and changing parameterization in the offline phase obviously is possible, because we can even run on the same clustering or microcluster summaries. We can run multiple algorithms, because this is completely offline. Yeah? So this has nothing to do with the constraints of the streams. Only the online component is subject to the stream limitations and the stream constraints. So here are the basic microcluster models or methods. So one of the first, and historically the first microclusters are the so-called cluster features. They have originally been, here is the original reference, have originally been proposed in the database community as a speed up for data clustering, for batch clustering methods, actually, yeah, for very large data sets, where the authors argued that for very large data sets, it is okay if you get an approximate clustering, even in a batch scenario. Yeah? And they proposed to summarize a set of data points x by three values, actually. So nx is the number of points in the set of points. So you summarize a set of points. So you summarize how many points are in that set. You summarize the linear sum of all points. So you just sum up all the feature values. So LSX is, if the points are d-dimensional points, then LSX is also a d-dimensional summary. Yeah? And SSX is the squared sum of all points. So it's the same like the linear sum, but it's the squared sum of all of the points. Yeah? And why do you do that? Because from those three things, you can easily compute basic statistics about x, like the mean, which is the centroid, so that is probably needed with k-means, but also compactness measures like the radius, the diameter, variance, standard deviation, and stuff like that. Yeah, for all that stuff, you just need the linear sum, the squared sum, and the number of points. So that is the idea or the rationale behind that. And the most important point is that those clustering features have a very nice property, which is additiveness. Yeah? Which means for two given sets of points, x and y, their corresponding cluster features can be computed, or if you have two sets and you want to combine them, So you can compute the combined cluster feature by simply adding the individual cluster features. Yeah? So the cluster features for the merge, for the union of x and y, can be just computed by taking the cluster features of x plus the cluster features of y. That's why it is additive, meaning that the number of points in x is just the number of in x union y is just the number of points in x plus the number of points in y. Makes sense? And the same holds true for the linear sum of x union y. Is just the linear sum of x plus the linear sum of y, and the same holds true for the squared sum, obviously. Yeah, and that is a very important property. Why is that? Because it means that if you have a cluster feature x of a set x and you want to add a new point, you just have to add the point. You just have to add 1 here for the number of clusters. You just have to add the point to the linear sum, and you just have to add the point squared to the squared sum. Yeah? So maintaining the cluster features for incoming data is very, very efficient. You just have to compute 3 sums actually, which is extremely efficient, obviously. And there are so that are the original cluster features, and there is a different type of cluster features proposed for density-based clustering, especially for optics, which is called the data bubbles. So the idea is that cluster features are good for the partitioning-based clustering, especially K-means and their variants, of course, but they do not really capture density estimations, which are necessary for density-based clustering algorithms, especially for optics. In that case, authors proposed the so-called data bubbles for a set of points. So they propose to grab some different statistics. Nx is the number of points, mx is the centroid of x, which can be computed from the CFs if you want. But now Rx is the radius of the ball centered at the medoid and capturing all points in X. Yeah, so the extent, so to say, of this set of points. Yeah, and so that's why it is called a data bubble, because it's considered to be bubbles here. Yeah. Data bubbles can obviously be computed for CFs, but now data bubbles, the big advantage of data bubbles is that they are also allow a good approximation of the things that are computed by the optics algorithm, which is basically the core and the reachability distances. Yeah, so have a look into optics to see what that exactly means. So those things are needed or are computed during the optics run. The optics needs to compute those 2 values in order to decide where to go next, which object to process next. So those things are needed especially for hierarchical density-based clustering.